Welcome back to ChemDoctor, and this is the second video in the series on orbital diagrams. Alright, now, in the first video what I did was I laid the groundwork for the difference between an electron configuration and an orbital diagram. I talked about the four quantum numbers, the importance of the magnetic spin number being the fourth quantum number defined by Pauli's exclusion principle, which says that no two electrons can have the same four quantum numbers, and then we started practicing with some orbital diagrams. So what I want to do in this presentation is literally just do some orbital diagrams. All right. So what we're going to accomplish here is we will start with lithium, and we're going to walk across period 2 on the periodic table. And as we do that, I'm going to illustrate how you write the orbital diagram, and I will again reiterate what's called Hund's rule, which says that the lowest energy configuration of any atom is the one with the most unpaired electrons, and we will just review and solidify drawing these diagrams. So remember, the main difference between a configuration, electron configuration, and orbital diagram is that the configuration tells you or gives you information about the energy level of the electron and the shape of the orbital it's in. The orbital diagram gives you information about all four quantum numbers. Now, the best way to proceed with an orbital diagram is to always write your electron configuration first. So for lithium, the configuration is going to be 1s2, 2s1, and then normally what I do right next to that is produce the orbital diagram. Now you're going to have a platform for each of the suborbitals, which has to be properly labeled. All right, so we see that for the 1s shell that we've got 2 electrons in there, so I'm going to put those in. I prefer to use half arrows, all right, rather than the full arrows. And I always, by convention, go with when they're paired up, go with my first arrow up, the second one down. Although in the first presentation, I made the point that we actually don't know which direction the electron's spinning, number one, and having the arrow pointing up or down doesn't mean anything about right or left. And then we see for the second electron, which happens to be our valence, that it's in the 2s shell by itself. By convention, I'm going to put that in with a single arrow pointed up. All right, and again, to reiterate, when you look at this, you can see all four quantum numbers for each electron. So take this one here. We know which energy level it's in. It's in energy level 2. We know the shape. We know the L number for this. The ML number is implied right here by the platform. There's only one orientation, and the arrow pointing up or down indicates that the electron has a specific spin, either to the left or to the right, or clockwise or counterclockwise, depending on how you look at it. All right. Now, the next element to the right of lithium will be beryllium, atomic number 4. Its configuration will be 1s2, 2s2. All right. Orbital diagram. Platform for each suborbital, proper labeling underneath. There's a doublet on the first platform and a doublet on the second. So we see that we've got paired electrons in both the 1s and the 2s. All right, now we're going to move to boron. The atomic number is 5. The configuration will be 1s2, 2s2, 2p1. All right, and we'll clean this up a little bit. Okay, now the orbital diagram will have a platform for the 1s, a platform for the 2s. Now remember, when you get into a P series, there will be always 3 platforms. All right, and this, let's get our labeling. This will be the 1s, this is the 2s, and then I just use a bracket like this to indicate that all 3 of these platforms are P system. Each platform represents a specific orientation, which could be in the x-axis, the y-axis, or the z-axis. And there's no order relative here. So in other words, this first platform is not necessarily the x orientation. All we're doing is acknowledging that there are different 3 different orientations for the p system, and each orientation will hold a maximum of 2 electrons. All right, so in 1s we're going to have a doublet. The 2s has a doublet, and then our 2p system we have a single electron, and I'm going to fill moving left to right, and when we have to pair up I come back to where I started and then go forward again. So this is the way I would write the orbital diagram for boron. All right, carbon's next, 6, so we have 1s2, 2s2, 2p2. Orbital diagram. Here's my 1s, here's the 2s, bracket, 2p. All right, we have a doublet, doublet, and then I've got 2 electrons to go. Hund's rule says that the lowest energy configuration for any atom will be the one where we maintain the most unpaired electrons. So do not pair these up. That second electron is going to go here. Now, to be technical about this, I could have placed it in the last platform too. Like I said, by convention, I usually fill left to right, and then when we have to start pairing up, then I'll come back to the front and move right again. All right, so that was carbon. Now nitrogen. 2s2 and then 2p3. Right, and just a reminder here as we go through this, I'll go ahead and underline my valences for these, and look at this guy here. 3 and 2 is 5, and you find nitrogen in group 5a. All right, now the orbital diagram. So we have a platform for the 1s, one for the 2s, and then 3 platforms for the 2p. Proper labeling. Now we can put the electrons in. All right, and there will be 3 here, and do not pair any of them up. They go in as singlets, like that. Okay, you could have put them pointing down. That doesn't matter. The issue is that they should the arrow should each have its own platform. Now we see where Hund's rule comes into play in a bigger way. So for oxygen, it's going to be 1s2. 2s2, 2p4. The orbital diagram. All right, so we're going to have, let's see, the 1s here, the 2s. Here's my 2p. We have a doublet, doublet. Put my singles in. And then we still have 1 electron to go, so I'm going to put it here. Again, coming back to the right, and then if we had more electrons, we'd continue moving to the right. So this indicates that oxygen has got, in its outermost energy level, it has 2 unpaired electrons. Nitrogen, in its outermost shell, has 3 unpaired electrons. Carbon, in its outermost shell, has 2 unpaired electrons. Boron, in its outermost shell, has 1 unpaired electron. All right, let's move to fluorine next. Configuration, 1s2, 2s2, 2p5. All right, now here's my orbital diagram. Proper labeling. We're going to have a doublet here, and then we're going to have, let's see, 1, 2, 3, 4, 5. So this is what the outer shell of outermost orbitals of fluorine are going to look like. We're going to have a single unpaired electron in that condition. Right now, if we look at neon, 10. All right, 1s2, 2s2, 2p6. 6, 7, 8, 9, 10. So we see energy level 2 is completely full in this case. My orbital diagram. Proper labeling. All right, the electrons go in. We have a doublet here, a doublet here. And this guy is totally full, so my next electrons come in pointing down. Again, to reiterate, no two electrons can share the same 4 quantum numbers. In order for 2 electrons to be in the same suborbital, they have to have opposite spins, because that way they operate as little magnets. The force of magnetic attraction offsets the net repulsion caused by the fact that the 2 electrons have the same charge. All right, now let's just keep moving. The next element, so we're going to step all the way back left across the table into period 3 for sodium. So its configuration will be 1s2, 2s2, 2p6, 3s1. There's 11 electrons. Outer valence is here. All right, and let's look at our orbital diagram. All right, let's hit the labeling. We got 1s, the 2s. These 3 platforms are the 2p, and we have a 3s. All right, we have doublet, 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 and a single electron out here in the 3s shell. All right, let's look at magnesium. 1s2, 2s2, 2p6, 3s2. So again, the orbital diagram. Get my labeling. All right, and this is what it's going to look like. Okay, now we're going to make a big jump, because what I want to do is show you what happens when we get to something that's got d orbitals in it. So let's go to scandium, okay, which has got 21 electrons. And its configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6. And then just in case you're wondering, if we do a quick count, we're 18 to here. Then we're going to have 4s2, and then we're going to have 3d1. All right? So let's take a look at what the orbital diagram is going to look like for that. And this is based off of the more extended electron configuration, which I think very quickly I'll put up here at the very top of my presentation. So it's like this: 1s2, 2s2p, 3s3p, 4s3d, and then 4p. And that gets us all the way to krypton from hydrogen. All right? That has a total of 36 electrons. All right, so let's look at the orbital diagram for this. I'm going to have to put it underneath because it's going to be so big. So first off, we're going to have the 1s, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, and then the 3d. Now let's see if I got them all. So this is the 1s, the 2s, the 2p, the 3s, the 3p, the 4s, and then 5 platforms for the 3d. So remember, your d orbitals hold a maximum of 10 electrons. That means there has to be 5 suborbitals: 1, 2, 3, 4, and 5. All right. So now we go ahead and place the electrons. We have a doublet in the first position, a doublet here. In fact, we got doublets for a long time. So I'll just run them out. 4s, there's a doublet, and then we have a single electron in the 3d. Now, just for you just so you can put this in your pipe and smoke it, I want you to realize that right here, this is your valence for a period 4 element. So it's going to be the 4s plus whatever's in the 3d. All right, and with that, I'm going to go ahead and close the video.